Right now, the entire future of computing depends on one of the strangest machines humanity has ever built. A machine that fires droplets of molten tin through a vacuum chamber 50,000 times every second, and blasts each one with a laser just to create a flash of invisible light that lasts a fraction of a microsecond. That flash is the only reason the most advanced chips on Earth exist. And here's the part almost nobody talks about. After all of that violence, less than 0.1% of the electricity going into the machine ever comes out as usable light. It is, by a wide margin, the most inefficient way to make light that we have ever industrialized. And we do it anyway because there is no alternative, except now there might be. There is a second way to make extreme ultraviolet light, and it does not involve tin or plasma or explosions. It involves electrons moving at almost the speed of light inside a particle accelerator. ASML looked at that idea years ago. They looked at it again more recently, and both times they walked away from it. Right now, 3 different countries are picking up the thing ASML put down, and each of them is doing it for a completely different reason. The Americans want it small enough to fit next to a fab. The Japanese want it efficient enough to be affordable. And China wants it because they are not allowed to buy the alternative. That last one is the story. Because China is not trying to squeeze a particle accelerator into a chip factory. They are designing the chip factory around the accelerator. Subscribe to the channel and let me explain. Most people still think the AI race is a fight over GPUs. It isn't. The real bottleneck sits one layer below that. And it is light, because a modern chip only exists if you can reliably print nanoscopic structures onto silicon over and over billions of times without a single meaningful mistake. And the smaller the transistor gets, the harder that becomes. We are, at this point, etching rocks with invisible light and hoping physics cooperates. Lithography is essentially photography for computer chips. You generate an extremely precise beam of light. That light travels through a maze of mirrors, reflects off a photomask carrying the chip design, and lands on a silicon wafer coated with a chemical layer called photoresist. When the photons hit that surface, they chemically change the material in exact locations. At that moment, the design is printed. Then comes everything else: etching, deposition, doping, stacking layer after layer, until billions of transistors emerge from an ultra-pure slice of silicon, at least when everything goes right. But underneath all of that sits one brutally simple constraint: your wavelength. It defines how small your features can be. And eventually the industry hit a point where the light itself was larger than the patterns it was trying to print. For years, chip makers ran on deep ultraviolet light at 193 nanometers, and they kept pushing it into dimensions it had no business reaching. So engineers started inventing tricks. Take one complex pattern, split it into several simpler ones. Print the first half, etch it, expose the second half, etch it again. Suddenly you can create features smaller than the light should physically allow. This became known as multi-patterning. And this is where cheap manufacturing quietly turned into an engineering maze. Every extra pattern meant another mask, another alignment step, another opportunity to destroy a wafer worth more than a car. The industry was forcing old light to print features it was never designed to print, and eventually the workaround became harder than the problem it was solving. So ASML and the industry did something extraordinary. They jumped to an entirely different kind of light. Extreme ultraviolet, 13.5 nanometers, more than 14 times shorter than what came before. Small enough to print features only a few nanometers wide. It was one of the biggest technological leaps in industrial history. And generating that light pushed humanity straight to the edge of what physics allows. Here is what actually happens inside that machine. Microscopic droplets of molten tin fall through a vacuum chamber. A first laser pulse hits a droplet and flattens it, reshaping it for what comes next. Then the real hit arrives. A carbon dioxide laser running at over 10 kilowatts of average power slams into that flattened tin and vaporizes it into plasma. For an instant, that plasma radiates the 13.5 nanometer light that modern transistors depend on. 50,000 times a second. Every second the machine is running, and that laser is a monster in its own right. It starts with a seed pulse of just a few watts and then amplifies it more than 10,000 times across 5 amplifier stages until the peak power of each individual pulse is measured in megawatts. All of that aimed at a droplet of tin you would need a microscope to see, in a window of time so narrow that missing it means the pulse is simply wasted. And the machine cannot afford to miss because it has to hit the next 120 microseconds later. And the strange part is how little of it survives. Extreme ultraviolet light is absorbed by essentially everything, including air and glass, which is why the whole machine runs in a vacuum and why there is not a single lens inside it. There can't be. Nothing transmits this light, so the entire optical system has to be built from mirrors. And even those only work because they are coated with dozens of alternating nanometer-thin layers of molybdenum and silicon that reflect by interference rather than by simple reflection. Even then, each mirror gives back only around 2/3 of what hits it. Now chain roughly 10 of those together, add a mask that is itself a mirror rather than a transparent plate, and do the arithmetic. By the time the light reaches the wafer, the overwhelming majority of what you generated is simply gone. That is how you end up with a wall plug efficiency below 0.1%. Tens of kilowatts going in, a few hundred watts of usable light coming out. And that inefficiency is not just an accounting problem because there is a much nastier consequence hiding behind it. It's called shot noise. Below roughly 3 nanometers, fabs start running into what engineers call stochastic limits, which is a polite way of saying there are literally not enough photons landing on the wafer for the statistics to hold. Physics stops being deterministic and becomes probabilistic. Imagine spray painting a perfect line, except some of the paint particles randomly never arrive. At normal scales, irrelevant. At these scales, that is a killed transistor. And it gets worse as you go because the next generation of optics needs even thinner photoresist films, which means even fewer photons absorbed, which means even more randomness. ASML's own roadmap acknowledges this. Their Hyper-NA concept, the generation after High-NA, is targeting a numerical aperture of 0.75, and the estimated price is around $720 million per system, with visibility somewhere around 2030. But even there, an electron blur of roughly 2 nanometers inside the resist may impose a hard resolution floor no lens can fix. And every step up this ladder gets more expensive in a way that is hard to overstate. The workhorse EUV tool shipping into fabs today, the NXE3800E, runs at around 195 wafers per hour with an upgrade path to 230, holds overlay below 1.1 nanometers, and costs roughly $180 million. Step up to High-NA, the EXE:5200B, and you get a 0.55 numerical aperture and 8 nanometer resolution. 175 wafers per hour, 0.7 nanometer overlay. The price roughly doubles to about $380 million. The machine weighs 150 tons, arrives in 250 shipping crates, and takes something like 6 months and 250 engineers to assemble on site. And Hyper-NA, if it arrives, roughly doubles the price again. So the answer to almost every one of these problems is the same. More photons, more power, brighter light. Every generation of optics throws away more light than the one before it, which means the source has to keep getting stronger just to stand still. And that is exactly why, for the first time in over a decade, serious people are looking at a completely different way to make it. Instead of exploding tin, you use electrons. Now, this is where the story takes a genuinely unexpected turn, because a free electron laser doesn't work like a normal laser at all. A conventional laser uses atoms. You excite a material, the atoms drop back down and release photons, and you get a beam. A free electron laser skips the atoms entirely. It takes a beam of electrons, accelerates them to nearly the speed of light, and fires them through a long structure of alternating magnets called an undulator. Those magnets force the electrons to zigzag as they fly forward. And when a charged particle changes direction at relativistic speed, it radiates light. At first, that light is weak and messy, but then something remarkable starts happening inside the beam itself. The light the electrons emit begins acting back on the electrons. sorting them into tightly spaced groups, microbunches. And once the electrons are bunched at the scale of the wavelength they are emitting, they stop radiating as individuals and start radiating in phase together. The output doesn't grow a little, it grows exponentially. Tune the electron energy and the magnetic structure, and you choose your wavelength, which means you are no longer married to 13.5 nanometers. And that single sentence is why this technology is suddenly interesting to an industry that has built its entire roadmap around one number, because the ecosystem we have today is welded to that number. Every mirror coating, every mask blank, every resist chemistry, all of it optimized for 13.5 nanometers. A free electron laser is tunable by design. Existing FEL facilities already operate across a range that runs from terahertz frequencies all the way down into hard X-rays, well below a single nanometer. In principle, that opens a path to printing features smaller than what today's EUV can realistically reach, no matter how many clever tricks you stack on top of it. There is also a quieter advantage that matters more than it sounds. A tin plasma radiates across a broad spectrum, and the mirrors only reflect a narrow slice of it, so a large fraction of what the source produces is thrown away before it does any work at all. A free electron laser emits into a much narrower band by nature, which means a bigger share of the photons you paid for actually survive the trip to the wafer. Same argument as before, from a different direction. You are not just making more light, you are wasting less of it. And then there is the raw power argument, which is honestly the more practical one. A single FEL can generate far more extreme ultraviolet light than a single tin plasma source. In lithography, more light means faster printing, and if one source can produce kilowatts instead of hundreds of watts, you don't feed one scanner. You feed a whole row of them, routing the beam through a network of grazing incidence mirrors that skim the light along at shallow angles instead of bouncing it head-on. Precisely because that is the only way to move extreme ultraviolet across a building without losing it. This matters enormously right now because AI demand is not slowing down. Data centers are consuming advanced silicon faster than the industry can produce it, and leading-edge capacity is effectively sold out years in advance. A fab already costs tens of billions of dollars. Every additional wafer you push through it per hour is pure margin. So the question stops being academic very quickly. Can you build a light source that turns one fab into the equivalent of two? The strange thing is that machines like this already exist. They just weren't built for chips. And to understand what that actually looks like, you have to go to Hamburg. An ASML EUV scanner is famous for being enormous, roughly the size of a double-decker bus, 150 tons, arriving in 250 crates and taking 6 months and hundreds of engineers to assemble. Now hold that image and consider the European XFEL. It runs 3.4 kilometers from the DSY campus in Hamburg to the town of Schönefeld, most of it underground. The accelerator section alone is 1.7 kilometers long and contains 768 niobium cavities chilled to minus 271 degrees Celsius, 2 degrees above absolute zero. It pushes electrons to 17.5 gigaelectron volts, and it fires up to 27,000 X-ray flashes every second, which it achieves in a way that tells you exactly why superconducting accelerators matter here. 10 pulses per second, but each pulse carries up to 2,700 individual electron bunches. A normal accelerator has to pause between shots to shed heat. A superconducting one barely heats up so it can keep firing. It was never designed to print a single transistor. Scientists use it to watch molecules move, proteins fold, and chemical reactions happen in real time. It is essentially the world's fastest slow-motion camera for atoms. But semiconductor engineers started paying attention to it anyway because that repetition rate and that average power are exactly the kind of industrial photon output a future fab would need. Not a burst for an experiment, a continuous flood around the clock. And that is where the picture starts getting genuinely strange. Because if this is the direction things go, a future chip factory stops looking like a chip factory. Today, every EUV scanner makes its own light. Each one is an island. If one source fails, that tool goes down and the rest of the fab keeps humming. Replace all of that with one accelerator feeding 12 or 20 scanners through a network of grazing incidence mirrors, and you have built something new. Not rows of independent tools, but a fab sitting on top of vacuum tunnels, superconducting cryogenics, and a particle accelerator. Something closer to CERN with a clean room bolted on. The efficiency is beautiful. The fragility is terrifying. Because the moment your light source is centralized, one failure doesn't take down one tool. It takes down the entire factory. So how do you turn a national laboratory into factory equipment? That is exactly the question the American company xLight is trying to answer. xLight is based in Palo Alto, and its CEO and CTO, Nicholas Kelez, previously served as chief engineer for the LINEC coherent light source at SLAC, Stanford's National Accelerator Laboratory. So this is not a group of people learning accelerators from scratch. Their strategy is deliberately unglamorous. They are not trying to redesign the fab. They want to replace exactly one component, the light source. Keep the scanners, keep the optics, keep the process recipes the industry spent 20 years developing. Just delete the tin. Their targets are aggressive, 4 times more EUV power than current laser-produced plasma sources, roughly half the cost of EUV light, around 20% lower total wafer cost, and a single source feeding up to 20 patterning tools, instead of today's strict one source per tool. They also argue their beam is fundamentally cleaner, with a narrower spectral width and programmable characteristics that could eventually be pushed to shorter wavelengths. And this is no longer a slide deck. In July 2025, xLight closed a $40 million Series B led by Playground Global. On December 2nd of that year, the U.S. Department of Commerce signed a $150 million letter of intent under the CHIPS Act, and that award was finalized on June 2nd, 2026. Pat Gelsinger, the former CEO of Intel, joined as executive chairman in March 2026, and Thomas Caulfield of GlobalFoundries joined the board. The company is now reported to be raising around $350 million more, with Bain Capital and Boardman Bay Capital Management leading, and has lined up non-binding agreements for as much as $4.2 billion in project financing for the facilities themselves. The first full-scale prototype is targeted for 2028 at the Albany Nanotech Complex in New York. Read those numbers again because they tell you something. A single light source project is now attracting the kind of capital that used to build entire fabs. And when they say compact, do not picture something small. This is still a linear accelerator sitting next to a factory. It just isn't 3.4 kilometers long. That is the American answer. Shrink accelerator physics until a fab can live with it. Japan looked at exactly the same problem and decided the real enemy was something else entirely. At KEK, Japan's high-energy accelerator research organization, the argument is that size is not what kills you. Power consumption is. Normally in an accelerator, you spend enormous energy accelerating electrons, use them once, and then dump the beam into a block of metal. All that energy becomes waste heat. Their answer is called an energy recovery LINAC. Instead of dumping the spent beam, you steer the electrons back through the same accelerating cavities, but out of phase. As they decelerate, they hand their remaining energy back into the cavities, and that recovered energy accelerates the next batch of electrons coming in. It is regenerative braking for particle beams. And the effect on the economics is dramatic, because researchers there estimate this approach improves wall plug efficiency by something between 10 and 100 times compared to today's sources. Remember, today's number is below 0.1%. There is a lot of room. Their projected output is 10 kilowatts of EUV power. To put that in perspective, current production systems operate in the hundreds of watts. KEK's 2021 cost estimate put a new system at roughly $260 million to build, with about $26 million a year to operate, and they argued the per tool cost would land well below what laser-produced plasma sources cost today, precisely because one machine serves many scanners. And notice what the recovery loop really buys you. It is not just a lower electricity bill. Every watt you don't waste is a watt of heat you don't have to remove. And thermal management is one of the quiet reasons accelerators are hard to run continuously. Recover the energy, and suddenly you can run the beam far harder without the cooling system becoming the limiting factor. That is how you get from hundreds of watts of light to 10 kilowatts without building a power plant next door. But the honest caveat is that this remains a research program. There is no fab anywhere running production wafers on an energy recovery LINAC, and there won't be one soon. KEK has demonstrated the pieces, nobody has demonstrated the product, so America is chasing compactness, Japan is chasing efficiency, and China looked at both and decided to chase something else entirely, scale. Because for China, this is not an upgrade path, it is a hard strategic necessity. Export controls mean China cannot buy ASML's EUV systems at all. Not the newest ones, not the older ones. And without EUV, the only route to advanced logic is multi-patterning with deep ultraviolet tools. And it is worth being precise about what that actually costs you, because this is the heart of why China cannot simply shrug and carry on. A layer that one EUV exposure could print in a single pass might need 4 separate DUV exposures with an etch step between each one. So you are buying 4 masks instead of 1. You are running the wafer through the scanner 4 times instead of once, which means your effective throughput collapses. And every one of those passes has to align to the previous one within a couple of nanometers. So every pass is another chance to scrap the wafer. Yield falls, cycle time stretches, cost per good die climbs. You can absolutely build a 7 nanometer chip this way, and China has. Building it profitably at volume, generation after generation, while your competitors print the same layer once, is a completely different problem. So China is running at least 2 tracks at once, and they are very different from each other. The first track is the conventional one, and it is further along than most people assume. There is a domestic EUV prototype operating inside a laboratory in Shenzhen, reportedly completed in early 2025, with Huawei coordinating a network of companies and state research institutes. 2 competing source approaches are being pursued in parallel. One team, led by Lin Nan, uses solid-state lasers to hit tin droplets and has reported a conversion efficiency of 3.42%. Another, led by Zhao Yongpeng at the Harbin Institute of Technology, uses laser-assisted discharge-produced plasma, a different way of making tin plasma, and has reached roughly 100 watts. SMEE and Shenzhen SiCarrier are in the mix on the tool side. Beijing is targeting 2028 for actual chip production on domestic EUV, though most outside analysts consider 2030 the realistic date. And critically, that prototype has not yet produced working chips. But the second track is the one that matches the title of this video, and it is far more radical. It is called SSMB, Steady State Microbunching. And the concept came from Alexander Chow, an accelerator physicist who spent his career at SLAC. Tsinghua University has been running a dedicated task force on it since 2017, led by Professor Chuanxiang Tang. Here's the idea. A normal free electron laser is a straight line. You accelerate electrons once, run them through an undulator, extract light, throw them away, and start over. A storage ring is different. Electrons circulate continuously, going around thousands of times per second for hours. Storage rings are wonderfully efficient at keeping a beam alive. What they cannot normally do is keep electrons bunched tightly enough to radiate coherently, because the bunching smears out after a single turn. SSMB attacks exactly that. You use a laser to modulate the electrons and organize them into microbunches spaced at the scale of the laser wavelength, and you design the ring to be quasi-isochronous, meaning the electrons return to the same optical phase turn after turn. If you can hold that structure, then every single pass through the undulator produces coherent radiation, not a pulse. A continuous high average power beam. And it is not just theory. In 2021, an international team from Tsinghua working with Helmholtz Zentrum Berlin and the German National Metrology Institute PTB demonstrated the SSMB mechanism experimentally at the metrology light source in Berlin, using a 1064 nanometer laser and observed sub-micrometer microbunching with the optical phase preserved turn after turn. That result was published in Nature. In 2024, a follow-up paper in communications physics confirmed the theoretical foundation underneath it. So the physics has been checked in a real ring by multiple institutions across 2 continents. Now look at what they want to build with it. Tsinghua design targets kilowatt level average power at 13.5 nanometers inside a 2% bandwidth, which is the specific band lithography mirrors actually reflect. Early design work described a ring with a circumference of around 48 meters. More recent discussions with authorities in the Xiong'an area, the planned city southwest of Beijing, reference a machine somewhere between 100 and 150 meters around. And a related published design describes achieving roughly 2.5 kilowatts of average power at 13.5 nanometers from a compact ring of around 160 meters. Compare that to a current production source running in the hundreds of watts, and you can see why this is being taken seriously. But the number is not the interesting part, the architecture is. Because the plan was never to build one SSMB ring and sell it to a customer. The plan is to put the ring at the center of a facility and build the fab around it, feeding many scanners from one continuously circulating beam of electrons. That is a completely different theory of what a chip factory is. The American approach treats the light source as a component you swap. The Chinese approach treats it as the foundation you pour first. And there is a certain logic to that when you are starting from nothing. If you already own 15 ASML scanners, ripping out their sources and replumbing the light is a retrofit. And retrofits are painful. If you own 0, you are not retrofitting anything. You are laying out a greenfield site, and you can put the ring in the middle and design every beamline around it from day one. The constraint that makes this hard in Arizona is the constraint that does not exist in Xiong'an. Being locked out of the existing technology means you are also not locked into it. And I want to be careful here because this is exactly the kind of story that gets wildly oversold in both directions. So let me give you the counter argument, and it is a strong one. Critics point out that what has been demonstrated so far is an academic research machine, not a commercial manufacturing unit. A synchrotron of this class is over 20 meters across and enormously expensive. The full Tsinghua EUV ring has been described in their own materials as under study and seeking funding. And there is real historical precedent for this failing. In the 1990s, IBM tried to use a synchrotron for X-ray lithography, and despite genuinely working physics, the approach lost to optical lithography and disappeared. Working physics has never been enough in this industry. Which brings us to the most uncomfortable question in this entire story. If free electron lasers are so obviously better, why did ASML say no? Because they did evaluate it. Roughly a decade ago, and then again more recently, ASML weighed free electron lasers against continuing to develop laser-produced plasma. And both times they concluded the same thing. Tin plasma carries less technological risk. That decision looks conservative until you understand what a fab actually optimizes for. It is not elegance, it is uptime. A production fab runs 24 hours a day, every day, and the tool that wins is the one that is still running at 3 in the morning without freezing a billion-dollar production line. Scientific facilities schedule downtime. Fabs cannot. And then in February 2026, ASML made the argument a lot harder for everyone else. They demonstrated a 1,000 watt EUV source as a proof of concept. The technique uses 3 lasers instead of 1, 2 shorter wavelength pre-pulses to shape the droplet, and a CO2 laser for the main hit, running at 100,000 tin droplets per second, double today's rate. That is 50% more power than the best EUV tool currently in the field. And it targets throughput of up to 330 wafers per hour toward 2030, compared with roughly 220 today. And ASML's lead technologist on the source has said publicly they see a reasonably clear path toward 1,500 watts, with no fundamental reason they couldn't reach 2,000. Sit with that for a second because it quietly reprices everything. 4 times more power than a 250 watt source is a revolution. 4 times more power than a 1,000 watt source is a much harder sales pitch, and it has to be delivered by a machine nobody has ever run in a fab. The target moved while the challengers were still building. There is also the redundancy problem, and nobody has solved it. Today, a fab might run 15 or 20 EUV scanners, each with its own source. Lose one, you lose a few percent of capacity. Centralize the light, and you have concentrated your entire leading-edge output into a single accelerator, which means you either accept catastrophic exposure or you build a second accelerator you hope never to use. And that second machine has to be paid for out of the savings the first one was supposed to generate. And then there is timing, which may be the most decisive factor of all. The AI infrastructure build-out is happening right now. TSMC and Intel are expanding aggressively in Arizona. Leading-edge capacity is booked out years ahead. IMEC is installing ASML's most advanced high-NA system with a qualification target inside this year. The industry needs wafers immediately, not in 2035, and history is full of technologies that were technically superior and commercially too late. So the realistic picture is not that free electron lasers replace tin plasma next decade. It is that ASML keeps shipping, keeps pushing power upward, and the accelerator approach becomes the insurance policy the industry buys in case the physics wall turns out to be real after all. Unless you are China, where it is not an insurance policy, it is the only door that isn't locked. And that leaves us with a genuinely strange paradox. The transistor has been shrinking for 60 years. It is now a few atoms across, but the apparatus required to print it has grown from a tabletop optical system to a machine the size of a bus to a $380 million tool that arrives in 250 crates, and now, possibly, to a superconducting particle accelerator buried under the factory floor. The thing we are making keeps getting smaller. The thing that makes it keeps getting bigger. In an industry whose entire identity is miniaturization, that is a deeply weird direction to be heading. And if this path actually works, then printing the smallest structures human beings have ever made will require building some of the largest machines we have ever built. So here's what I keep coming back to. For 30 years, the answer to every lithography problem has been better optics. From here on, it may be better particle beams, and whoever gets there first doesn't just win a product cycle. They control the choke point everything else runs through. Do you think the industry sticks with tin plasma through 2040, or does the accelerator win? Drop your take in the comment section below. I read them. And if this one gave you something you hadn't seen before, the best way to support the work is to share it with someone who still thinks the AI race is about GPUs, and subscribe to the channel.